So I'll go ahead and get started. It's a real pleasure today to introduce, and a privilege to introduce Mason Stahl. Mason and I have known each other for the better part of 15 years, I guess now. I met Mason when he was just beginning as a graduate student at MIT. He and I were in Vietnam together on what was a very fateful trip for both of us. We both were doing a new project in Vietnam, which we had Mason's advisor, Charlie Harvey from the MIT Superfund group. We had Mason, we had Lex, we had a whole host of others. And importantly on that event, that's the time I met my wife, Quay. The day I met, Mason and I were together, and Mason and I have been very close ever since. And our kids are now friends together, and we have known each other a really long time. Mason is a really great hydrologist who has been at Union College now for 6 years, I believe.
Yep. He
finished at MIT and went to consulting briefly before deciding to come back to science a little bit more, but actually consulting probably helped him to be better at deadlines than I am. Mason is the responsible angel over my shoulder here typically. Has done a lot with data, and in particular, Mason and I have worked together on a Powell Center project with the USGS to integrate data across a huge range of places in the United States and abroad for arsenic, and have, among our Superfund projects, we have now several others we work together on. So with that, I will stop talking, and you can and get a chance to hear a little bit more about Mason. He's going to actually present work that from field samples that I collected with two of my senior thesis students, Manal Chaudhuri and Sarah Wilson, and also and many of which were analyzed and interpreted for isotopes by a senior thesis student of his, Jacob Abbott. So with that, I'll be quiet here and let Mason present.
Awesome. Well, thanks so much for the nice introduction, Ben. All right, I'm gonna screen share here. And one moment. Can everybody see my screen? All right, awesome. All right, well, yeah, thank you so much for having me here today and for the kind introduction. So today I'm going to talk to you guys about hydrologic insights into arsenic and uranium in the Northern Plains. And in particular, I'd like to just highlight the many colleagues who are involved in this work. So as Ben just mentioned, my senior thesis student, Jacob Abbott, really helped to advance this work. He went and collected samples as well. And then, of course, Ben and Ben's students were instrumental in this work as well. Okay, so today, what we're going to be talking about is hydrologic insights into arsenic and uranium in the Northern Plains. And this work is motivated by a number of research questions that I'm going to touch upon throughout today's talk. And we're going to be looking at all of this again through this hydrologic lens. And so the first question we're asking is, well, where does high arsenic and uranium occur in water across the Northern Plains? And then the next question we ask is, well, what causes the occurrence of high arsenic and uranium in water, in both surface and groundwater? And so that's getting at the kind of mechanisms. And then the next thing, once we know where we find it, or we have some idea of where we find it, we have a sense of what's causing it, how can we integrate that understanding to better identify areas that are at high risk more broadly? Because we, of course, can't sample every single location across the Northern Plains. Okay, so first I want to jump in after introducing these questions and say, well, why do we care, right? And so I think for many of you, this is going to be, review, but we care, of course, because arsenic and uranium are toxic elements. They're widely present in the environment, and they occur in our source water and our drinking water, both in the United States and around the world. And they lead to a whole host of health issues. So for arsenic, right, the EPA sets a guideline of 10 micrograms or parts per billion arsenic in our drinking water. And so that's the threshold that's, for the maximum concentration level. And this is a problem both in the United States and around the world. So globally, it's estimated that 140 million people are exposed to high arsenic in their drinking water. And in the US, we have more than 2.1 million people on domestic wells alone, so not even on municipal supply, but on their private domestic wells, who have groundwater concentrations that exceed the EPA guidelines. And that number expands when we consider community water supplies as well. So that's arsenic. Uranium, we similarly have issues. So again, it's widespread in the environment, and it's variable in our source waters and in our water supply. So here's some recent work by many of you who are on this call today. And this is showing a map from that recent publication looking at uranium and arsenic actually in community water systems across the US. And just to point out here, you can see the hotter or darker colors show community water supplies where the concentrations exceed the EPA threshold of 30 parts per billion for uranium. And so again, we can see many of the community water supplies across the United States have an issue with uranium in the water supply. In fact, this study found that around over 2% of community water supplies exceeded the EPA maximum threshold for uranium, and more than 2% exceeded it for arsenic. And so we can see this is a widespread problem, and it leads to a host of health issues in the communities and the people who are exposed to this. And so now I want to pivot and look at our study area and the data that we've collected and analyzed to gain a better understanding of arsenic in the Northern Plains. And so our study area is the White River watershed, which spans northwestern Nebraska and then into southwest South Dakota. And so on the map here, you can see, I'm kind of highlighting here in red, this is the Pine Ridge Reservation. And so it's a really large area. The White River watershed cuts through this area, and it has a population of 20,000 people. And we care about arsenic and uranium in this area because we know there are high concentrations in some of the source waters, and there's been measured high urinary arsenic and uranium. So there's exposure. And so largely the exposure is coming through arsenic and uranium in the groundwater supply that then people ingest. And so let's now zoom in a bit and take a look at the White River watershed. So I'm showing that here. It's outlined in the heavy black line, and we can still see the Pine Ridge Reservation shown in red. So the main stem of the White River, we can see snakes through the Pine Ridge Reservation and discharges and drains into the Missouri. So it's a really large watershed here. Though it's a fairly dry area, it gets about 17 inches of rain annually, so flows aren't always very high. And so what we're looking at here, the purple points indicate all of the locations that our group has sampled in 2021 and 2022 from surface water. So we've got 44 locations here that were sampled. And as Ben mentioned, right, him and his students went out and they've sampled a number of times, and showing some pictures here from their summer sampling in 2021, and they're collecting creek water. And then my student, Jacob Abbott, who worked on this for his senior thesis, he went out to the same area as well in the summer of 2022, and he collected a bunch of samples as well. And so I mentioned to you that a large route for exposure for arsenic and uranium is through drinking contaminated water, and oftentimes generally it's contaminated groundwater. And so I've said we're sampling here for the samples I'm showing you today are all surface water samples. So they're the main stem of the White River, some of the tributaries, and some nearby springs. And so you might ask the question, well, why are we sampling surface water if often the common route of exposure is through groundwater? And so I want to give a little bit of a primer on kind of the physical hydrology of river systems. And so surface water and groundwater, they're not separate entities, right? They are in constant interaction with one another. And so a couple of key concepts I want to introduce you to. So one is this concept of gaining versus losing rivers. And so I'm showing here in the left panel a kind of common configuration where we have our river here. So right, that's draining our watershed. And then that dashed line in the subsurface is the water table, or the elevation of the groundwater. And when we have a gaining river, that means that the groundwater levels are higher than the adjacent river. And that means that groundwater is flowing into the river, adding flow and adding dissolved solutes. And when those conditions prevail, we say that that section of the river is gaining. It's gaining groundwater. Okay, so when we have a gaining river, our river is essentially like a big well. It's a drain, and it actually, the water in that river is reflective in part of the groundwater chemistry because it's capturing groundwater discharge. And so this is why sampling surface water can give us insight really easily into the subsurface. Okay, but we also care because we're thinking about exposure, right? And so we can also have losing rivers. And a river, as it snakes downstream, can be gaining in one section and losing in another. And so a losing river is where the groundwater levels are lower than the river water level. And that means that water from the river flows into the groundwater. So if a river is losing, then the chemistry in the river is flowing into the groundwater and adding that to the groundwater. So either way, if a river is gaining in one part or losing, we care because it tells us about the groundwater system. It's either contributing something to the groundwater or it's reflective of the groundwater itself. And so this key point here is surface water and groundwater are not separate entities and they're constantly interacting with one another. Okay, so we collected samples from those 44 locations. Let's take a look at actually what we saw so we can better understand where we have high arsenic and uranium and then why we do, and then ultimately extrapolate to improve our understanding broadly about what's going on. Okay, so this plot here, I'm showing you on that, these are the samples that we collected and analyzed for arsenic and uranium, the surface water samples on the White River watershed. And the x-axis here shows uranium concentrations in micrograms per liter. The y-axis is showing arsenic concentrations in micrograms per liter. A couple notable things about this plot. So one is that many of our samples in surface water exceed the EPA guidelines or the EPA MCL, and they're above 10 ppb. And so that's what that horizontal red dashed line is. And so this is really actually a notable point, and something that surprised me when starting on this project is that you typically do not see concentrations that high in surface water. In groundwater, it's more common, but so it does highlight the connection between these systems. And so we have really high arsenic in many of our samples. And similarly, we have high uranium in some, and so that's the EPA guideline for uranium of 30 parts per billion. Another key point I want to highlight here is in all of our samples, you can see a somewhat positive trend, or rather, as uranium increases, so too does arsenic. And again, this is a somewhat notable feature of the White River watershed. It's atypical in terms of what we would generally expect, especially when we're working in areas that have really high arsenic like Bangladesh or Vietnam. We often would see an inverse relationship. And that's because in many cases, arsenic is mobilized under anoxic or low oxygen conditions, and uranium is actually mobilized under the opposite conditions, or oxic, where there's lots of oxygen present. So we have a little bit of a unique system here. And so want to understand and tease out, well, what's the mobilization mechanism? And so now I'm showing you here our same samples, but on the x-axis, we're looking at sulfur, total dissolved sulfur, which is largely sulfate. And on the y-axis, we're looking at arsenic concentrations. And so this is log scale on both axes. And I want to point out a couple of things. We can see a broadly positive trend here, except for these three highlighted points which occur in the Badlands. We largely see as sulfate increases, so too does arsenic. And so this is suggestive of oxidative mobilization of arsenic from sulfide minerals, which would be more consistent with why we see high uranium as well, because uranium is more mobile under oxic conditions. So we have a kind of unique system here. And so that, as I pointed out, that positive correlation is suggestive of oxic mobilization of both arsenic and uranium. And sulfate just gives us that nice indicator that it could be a sulfide mineral source that's oxidizing. Now, this is consistent with our understanding of the groundwater systems in this area, right? And so I've just highlighted, this is a USGS fact sheet looking at the redox conditions, or how oxic or how reducing the aquifers across the United States are. And I've highlighted in the blue square here, the High Plains Aquifer, which underlies part of the Pine Ridge Reservation. And the key thing I want to point out here is these pie charts for the High Plains, southern to northern High Plains. The white portion of the pie chart indicates the proportion of groundwater that was measured there that's oxic. And key takeaway here is, yes, the groundwater in the High Plains is largely oxic. So that would be consistent with this mobilization mechanism. Okay, so we see that we have high arsenic, we have high uranium, we have a sense of this mobilization mechanism, but now we want to understand a little more deeply, how are concentrations evolving as it moves downstream and it flows, say, from the headwaters in Nebraska all the way to the mouth of the Missouri, to the mouth of the White River and discharges into the Missouri. So we're going to track some water downstream and look at how things change. For these upcoming slides, I'm just going to show you arsenic because, as we've seen, arsenic and uranium are strongly correlated. And so the story stays the same for both parameters, but it's easier to just focus on arsenic. Okay, so here are the samples that Ben and his students collected in July 2021. And so I'm plotting them here just for the main stem samples. We sampled a bunch of the tributaries as well, but I want to try to track water as it moves from the headwaters in Nebraska and flows through the Pine Ridge Reservation. And so all those big circles are our points that we sampled on the White River. They're color-coded by their arsenic concentrations. So we can clearly see as the water moves downstream, arsenic concentrations are increasing. And we're going to take a look at why that might be happening. So that was July 2021. We can look at August 2022. These are the samples that my thesis student Jacob collected, and we get a very similar result as the samples from 2021, namely that as the water moves downstream, arsenic concentrations are increasing. Okay, I want to highlight that the color scales here are just different for the different years, just so you could see the change downstream. But the concentrations are quite high in both years. Okay, so let's track this downstream and try to understand why is it increasing as we move tens, 50, or hundreds of kilometers downstream. Okay, so here, those same samples, and we're plotting them versus distance downstream on the x-axis. And I chose the 0 point as our first sampling point from July 2021. And the y-axis is the arsenic concentration. So these are all our July 2021 samples. This plot confirms what we were just seeing. Arsenic concentrations are increasing downstream. We add those samples from August 2022, sorry. And again, we see arsenic concentrations. Those are the orange ones from August, again, increasing downstream. Couple of key things to note here. One, these arsenic concentrations are extremely high. This is the EPA guideline. So many of our samples, right, are above EPA guidelines. And one other thing to note is that this increase downstream is greater in August 2022. And I'm going to talk about in a minute why that might be reflective of the difference in hydrology between those 2 years. 2022 was a much drier year, or for that period, than 2021 was. Second thing I want to point out is if we look at locations that are on the same distance downstream, those are the same points on the river that were sampled in 2 different times. So for instance, right here, we have same location sampled in 2021 and 2022, and then same thing here. And you can see how the interannual variability, the variability between years is great too. It goes from like 15 ppb to over 50 ppb. So we can see that between years, right, there's significant increases too. Okay, so let's kind of dive into this a bit more. We see arsenic and uranium increasing as we move downstream. And we'd like to understand why are these changes happening? So what's driving these changes? All right, so let's look back to our physical hydrology a bit more. What could cause arsenic concentrations to increase and uranium concentrations as we move downstream? And so if we take a look at that gaining system that I talked about earlier, right? If we had a section of the river that's gaining, then we could have high arsenic and uranium groundwater, seen here, that's discharging into the stream and continuing to add arsenic or uranium that's dissolved into the river. And so that could cause increases as the water moves downstream. Namely, we just keep adding a source, a higher concentration source. Another thing that can happen is that water can evaporate. And so even if we don't add more arsenic or uranium, if we started with an initial concentration and then we evaporate half the water, we've doubled the concentration because we have the same mass of initial arsenic and uranium. And if we evaporate water, we concentrate, right? And so that's there's these 2 mechanisms that can happen when we're on a gaining section of a river. Then on a losing section of a river, we don't have groundwater coming in, but we can still, of course, have evaporative enrichment. So key point here is that a river can be gaining in one part, and then you can move downstream and it can be losing. And there's really 2 mechanisms that can happen to increase concentrations. We could have evaporative enrichment, or we could have a new source being added from groundwater discharge. There could also have tributaries, but the tributaries are fairly low flowing. And I will talk about that. That's something we need to look at further in a little further detail. Okay, so from a physical hydrology standpoint, how can we see if a stream is gaining or losing? So what I'm showing here is our sample points from July 2021. They're color-coded by arsenic. But I also want to highlight something here. If you look where my cursor is, I put there's these purple points on the river. There's 4 of them. Those are USGS stream gauges. Those are locations where the USGS has a sensor and they measure the flow in the river every single day continually. And we can access that data. It's freely available. And so if we know flow as the river moves downstream, we can see is flow increasing, decreasing, or staying the same. And we can get insight into how much water is being gained or lost. And so I pulled the data for July 2021, the mean for that month, the total flow or the mean flow for that month. And each of these points is as we move downstream, the drainage area increases and we can look at flow. A couple of key things I want to point out. So these first 2 points are reflected on the first 2 points on this graph. We see that this is very low flow, less than 25 cubic feet per second, which is very low for a drainage area this big. In between these 2 sites, we nearly double the drainage area and flow barely budges. So it's minimal gaining. So there's probably there's probably not a ton of groundwater coming in, and there might be a lot of evaporation that's keeping flow low even as groundwater comes in. We do see flow increase as we move further downstream, a much bigger step increase, and then a more gentle one. So this river would be considered in July 2021. It was gaining along all sections, but it wasn't gaining very significantly across 2 out of the real 3 sections here. And so we could have both an input of a groundwater source and evaporative concentration. Now let's look at August 2022. We have the same flow locations, but obviously different flows for that year. And we can see from the first to the second flow location on the main stem of the White River, we actually, the basin doubled. We moved downstream, but flow went down. So that was clearly losing. So surface water was going into the groundwater and bringing any of the chemicals it has in it with it. And there was likely a lot of evaporative concentration too. We do have a slight increase in flow between the second and third gauge. So there's some groundwater that's entering probably here. And then we have a decrease in flow from the third to fourth gauge. So again, it's losing. So the hydrology was a bit different from August 2022 and July 2021. And this is probably reflective in the difference that we saw in the chemistry. August concentrations in 2022 were much higher than July. And so we probably had more opportunity for that concentration to happen via evaporation. So I want to just now dive in a bit more, and I'm suggesting that evaporative enrichment could be a process that's driving the increase in concentrations. But how can we actually know that? So to better understand that, let's look at some other chemical constituents and see if they also increase as we flow downstream. Remember, if water is evaporating, we're losing water volume and we're concentrating whatever was in there. So if arsenic is increasing because of evaporation, other things should too, like say sodium or chloride. So let's take a look at sodium, which is a fairly conservative tracer. It won't really precipitate out. And if we look at distance downstream for our July and August 2021 and 2022 respectively, we also see that the sodium concentrations are increasing. And we see that August 2022 has higher concentrations of sodium, consistent with that drier year where we probably had more concentrated evaporation. Okay, so this is consistent with evaporation, but it doesn't prove the point, right? It doesn't, end the story here. And so I want to now rely on water isotopes. So isotopes of hydrogen and oxygen of the water molecules themselves to better understand what could be going on here. This is a really powerful tool, stable isotopes of water, because they change in relation to evaporation, and we can actually model that. It's a very well understood process, and we have theory that dictates how isotopes of water will change as water evaporates. And so let's just do a quick primer on what are isotopes of water and how can we rely on them. Okay, so water isotopes, water is made up of hydrogen and oxygen atoms. And the dominant oxygen isotope is oxygen-16, has a mass of 16, and the dominant hydrogen isotope has a mass of 1. And so the most common molecule of water you're going to find in the environment has a mass of 18. However, there are isotopes of hydrogen that have an atomic weight of 2, and isotopes of oxygen that have an atomic weight of 18. And so we can see that in the environment, we can also find isotopically heavier water, right? And water can range from a mass of 18 to 22. And what's really great is when we collect a water sample, we can bring it back to the lab and we can measure the isotopic ratios of the heavy and light isotopes. And this is of the water itself, which is fantastic because it doesn't change except for things but like evaporation. It's a non-reactive thing. They're stable isotopes. They're not radioactive. They don't change except really in the face of evaporation. And they also encode or capture information about where the water originally came from, because precipitation from different times of year has a different isotopic signature. So this is something we can measure in our lab, and my student Jacob measured it on all of our samples. And so I just want to give you a little intro into what that kind of looks like. So here I'm showing kind of winter precipitation. This is like a cartoon or conceptual diagram. And this is oxygen isotopes on the x-axis and hydrogen isotopes on the y-axis, and then summer precipitation. And so the key takeaway here is that there's a seasonal signal in rainfall in many parts of the world, and it's very predictable. And winter isotopes are generally lighter, and summer isotopes are generally heavier, okay? And then surface water is typically a mixture of these things. And so we can look at the surface water, and we can often get an understanding of how much snow melt it's composed of versus how much recent rainfall. But what's really powerful is, in this case, we're interested in teasing out evaporation, right? And understanding how much evaporation happened or was evaporation happening to concentrate the stream water. And so when we have evaporation, it does not fall on this nice mixing line, right? So when we mix two water sources, they'll mix on that nice mixing line, that linear mixing line, but evaporation causes the remaining water to deviate from that line at a lower slope. And so an evaporation trajectory, this is, would look something like this. The lightest water evaporates and goes back to the atmosphere, and the water that remains in a pond or a lake or a river becomes progressively isotopically heavier as the lightest stuff evaporates. And so you can imagine after 10% of evaporation, the water would shift isotopically in the river. And then the river keeps evaporating and it keeps getting isotopically heavier and heavier. And so this is fantastic because this is we understand this process theoretically, and we can model the trajectories and really see, well, how much evaporation happened. And so I'm going to show you some modeling that we did based on our actual observed and measured samples of isotopes. But I just want to introduce one last concept here, is that there's a really handy thing we can do, is this concept called d-excess. And basically what d-excess is, I'm simplifying it a little bit here, but it's sort of the distance between my sample and that mixing line here, or the precipitation line. And as water evaporates more and more, that vertical distance between those two lines grows, and it grows more negative. And so we can actually see, we can calculate this metric of d-excess on our samples just to get a quick kind of assessment of how affected it is by evaporation. So as a first pass, we did that. And now I'm showing you our samples from July 2021 that were collected on the main stem of the White River. The x-axis here is our d-excess. And I just want to situate you. The left, as you move to the left, d-excess becomes smaller or more negative here, and that's consistent with more evaporated. And when you move to the right, that's or the larger numbers, that's consistent with less evaporation. So what do we see here? As we move up and to the left, arsenic is increasing and d-excess is decreasing. And that suggests that as our water is becoming more affected by evaporation and more concentrated by evaporation, as indicated isotopically, we also see arsenic increasing. So that's a nice indicator here, an independent kind of theoretical approach to look at, well, is the increase in arsenic because we just added a whole new source of arsenic, or is it because there's a evaporative concentration? And so it looks like at least part of it is evaporative concentration. When I throw on the samples here from our August sampling, we can see it's, again, still consistent here. They have very low d-excess and very high arsenic. So this is giving us this idea, the kind of now more theoretical insight into the fact that as the White River moves downstream, we get arsenic increasing, and in part, that's probably because of evaporative concentration. And so now the question you asked, and I was almost a little skeptical when we first started doing these calculations, is this feasible? Can we have evaporation like this in a river? And so we're in an arid area. The summer, it's very low vapor pressure or high vapor pressure deficit, so lots of evaporation. But let's look at what the river looks like. So here are some photos that my student Jacob took when he was sampling. And here was his first sample on the main stem of the White River. It's a somewhat deeper water body. And we can see here, that would be the starting point for his sampling. And remember, arsenic increases as he moved downstream. So then this is the photo he took at the second location. We can see that the water column is getting much shallower, which means that it's much easier to evaporate a high proportion of it, right? If we have 1 inch of evaporation per, say, week, and you only have 2 inches of water, within a week, you've evaporated half of it. A deeper river is much harder, even at that same inch of evaporation. If it's 10 feet deep, you've only evaporated a small fraction. So as this channel gets shallower and shallower, it's much easier to quickly concentrate the water. Oops. Oh, sorry. Did you have a question, Ben, or? Sorry, I saw it in the chat.
No.
Okay. Can you guys see the slides okay? Sorry. Yes.
Yes, perfect.
Okay, perfect. So then we move further downstream and we can see this third location, and now the far downstream, and the river is very shallow, right? And we can see that evaporative concentration would be very feasible here. Okay. So I'm going to show you my our modeling approach to quantify and get a sense on how much evaporation could have happened. And also feel free to chime in if you have questions or something's not clear on a slide. I'm happy to address it. Okay, so how could we quantify evaporation? So here I'm showing we can take 2 points on the stream, an upstream and a downstream location, and we can essentially track that parcel of water. We can say, all right, I'm starting here in the upstream location, and then I'm moving downstream, right? And I know the isotopes at the upstream and downstream location because we collected samples and we measured them in lab. And then we can apply the theoretical model for evaporation. And we can say, start with the upstream concentration and then run our model for evaporation and then see where it lands on our downstream sample. And so this colored line here is showing the trajectory that would have happened from evaporation. And it's color-coded by the fraction of water that had been evaporated away. And so I can see when it hits here, this would be like, oh, 30% evaporation. And so we can do this for every single pair that we had on the river. And so this is really powerful because now we're going to be able to get an isotopic approach to quantifying the amount of evaporation that happened. Then we can compare that against the change in concentrations that we observed between any two pairs of samples. And we can say the change in concentration could be due to evaporation, but it could also be due to a source. And so we can say, well, how much happened likely from evaporation we can get from isotopes. And then we can look at the measured chemical concentrations of arsenic, uranium, sodium, and we can say, how much enrichment did we have there? And that could be from both evaporation and an input of a source. But what's really nice here is by modeling the evaporative effects, we can see how much of the change in concentration could be attributed to evaporation. And so we did this evaporation modeling for a bunch of pairs of samples on the river. And now I'm going to show you those results and kind of contextualize them. So here on the x-axis, I'm going to plot every pair of samples, the modeled fraction evaporated based on our measured starting isotope and our measured ending isotope from the upstream and downstream sample. And then I'm going to show on the y-axis the evaporation that we would have calculated it to take to get the concentration that we end with. So for instance, if we start with 5 ppb arsenic at the upstream and end with 10, that would mean that we had doubled our concentration or evaporated half of our water, right? And so we can use our concentrations of, say, arsenic to say what's the hypothetical evaporation that could do that. And then we can validate it and say, well, how much do our isotopes tell us evaporation happened? And so I have this one-to-one line because for every sample, we can get a value on the X and a value on the Y. And if evaporation could explain, so the x-axis, if it could explain all of the enrichment in the concentration, it would fall on this one-to-one line. And so that would be, hey, that's the evaporative effect, and it explains all of the change in the concentration of arsenic or all of the change in the concentration of uranium. If, on the other hand, we have an additional source input, then we can say, okay, well, this sample hypothetical sample I show, it had about 35% evaporation, but the concentration of arsenic increased as if it had 60% evaporation. So we could say, well, 35% of that, of the 65% came from evaporation, and the remaining was some source input, maybe groundwater discharge, maybe a tributary coming in. And so now we actually did this for all our pairs of samples. So I'm going to show you what happens for our arsenic data. So we did it for a bunch of pairs of samples, and we calculated the fraction evaporated based isotopically, and then what we would estimate based on the increase in arsenic. And so we can see a couple of key things. They largely agree, actually. And in fact, we have anywhere from 25 to around 60% evaporation that we based on isotopic calculations. And our arsenic increases in concentration are a bit higher than just evaporation alone. So what does that suggest to us? Well, there's some uncertainty in these measurements for sure. But also it suggests that evaporation can explain some, but there's probably some additional source of arsenic coming in, say from groundwater discharge or tributaries. Now on those same pairs of samples, we can do the exact same thing, but we can do it for uranium. Remember, so you're going to see the X points are going to be identical, but now I'm going to do that same. What's the estimated evaporation based on the change in uranium concentration for those same points? So now I'm showing those in blue, and we can see similar story. Evaporation can explain a large part of the uranium increase in concentration, but not the whole thing. So for this point here, if you can see my mouse, evaporation from isotopes and the change in uranium concentration fall in the one-to-one line. So evaporation could explain all of that change. Same thing with that point. As we move north of the line, above the line, then it suggests that there's also some potential source input here. Okay, and then we did the exact same thing for sodium, right? Sodium actually falls pretty close to the line, and maybe that's not super surprising because it's a fairly conservative tracer, right? It doesn't react as much as arsenic or uranium. But I think the key takeaway from this figure here is that one, in this system, in this climate, in this river, which is fairly like low flows for a large river, we can actually have significant evaporative concentration. And that's reflected both isotopically and both chemically in the concentrations of contaminants like arsenic and uranium. Okay, so I want to tie all this together and just wrap up with a few conclusions here. So we see arsenic and we see uranium, and they're increasing as we move downstream. It looks like evaporative effects can more than double our concentrations. We can have at least up to 50% of our water can evaporate as we move tens or hundreds of kilometers downstream. And so that's actually a really, I think, notable thing and unique. We can have initially safe water that's below the EPA guidelines, as we saw in our upstream, some of our upstream samples. We could have no additional source of arsenic added or uranium. And due to evaporation alone, it could concentrate that water sufficiently so that it exceeds EPA guidelines, often by, in this case, by maybe a factor of 2 or 4 or 5. We also saw another really interesting thing is that arsenic and uranium in the White River can vary by a factor of 3 or more between years. So at the same point in the White River, if you sample it 1 year, you could have relatively low arsenic that's at or near the EPA guidelines. If you sample it the next year at that same location, you could have arsenic concentrations or uranium that exceed EPA guidelines. So the interannual variability, which appears to be largely driven by interannual variability in the climate or weather, can cause significant changes in concentration. Again, this is independent of an additional source, though of course we can have additional sources coming in from springs and tributaries. And then a really important takeaway that I'm going to then talk about in just for a few minutes, and that's going to relate to some planned future work, is that arsenic and uranium concentrations were closely related to the stable isotopes of water. And so this is really powerful because we saw how we can use stable isotopes of water to understand the hydrology and the physical hydrology better, and then link that to the chemistry that we observe. But what's really great is when we have stable isotopes of water being so strongly correlated to these concentrations, it also means that they're a great predictor of arsenic and uranium concentrations, at least at this kind of maybe local to regional scale. And so some potential future work is connecting isotopes in groundwater, right? Which we have a pretty good understanding of, to make predictions. So we could make broad predictions, point-based predictions across this whole area without necessarily having to go and sample everywhere. And so I just want to highlight how we might do that. So some past work I've done with my students and colleagues has been looking at isotope hydrology of the aquifer systems across the United States. And so I'm showing here a groundwater isoscape. And so this is just, we modeled isotopic concentrations of groundwater, shallow groundwater, across the entire United States. And so we have this data product available now. And what's really nice is we can now use this as a predictor or an input into a predictive model for predicting arsenic and uranium across the region, because we have this nice continuous surface that tells us isotopes in groundwater. And since it's so strongly linked to the arsenic and uranium concentrations, this would be a really powerful predictor for a future model. And so you can, if you go to that link there, you can see the paper and the data associated with this. And so we've already had some success making predictions of arsenic, but without using isotopes. And so we're going to add isotopes because it's such a strong influence here. And I just want to kind of key you guys in very quickly into that point. And so we've had a lot of success doing this in Cambodia. And so Ben and a postdoc of Ben's, Craig Connolly, as well as a student of mine, Beck DeYoung, we had a project that we wrapped up about a year ago, making predictions of arsenic in groundwater based on satellite imagery alone. And so we were looking at the flooding occurrence. And so I'm showing you a map here of Cambodia, and the darker blue colors are areas that flood frequently. The purple is intermediate flooding, and then everything else is not an infrequent flooding. And so I just want to highlight a key point here is that the flooding controls the redox characteristics of the soil, and that controls arsenic mobility. And so we saw, just looking at this map, where we have when we understand the occurrence of flooding on an annual basis, we're actually able to then take that information and make really good predictions of where arsenic in groundwater occurs. And we match this up to thousands of wells that Ben and others had sampled across Cambodia, which are shown as the colored dots here. And we link that to our understanding of the flooding occurrence. And I'll just show you. And we were able to predict groundwater concentrations really well. So this was observed groundwater on the x-axis and our modeled groundwater based on a model that relied on just the flooding occurrence and recurrence. And that was a really strong predictor. And so we can apply some of that understanding to this region. And then we can also link it, as I mentioned, to the isotope work, which will further boost our understanding. And so hopefully we can make predictive models that way. And so with that, I would like to wrap up. And if there's there's time for questions, I'd be happy to take them. Thank you.
Wonderful.
Oh, thank you.
Yes, this was really, really wonderful you explain it so clearly for all of us who are not hydrogeologists. I think you can see the public health scientists nodding. This was amazing.
Oh, well, thank you. Thank you very much.
Mason, I'll start with a question while others think of others. Sure. First, I just want to make a clarification that, and this is for Ben and for you, no one's drinking the White River water as a source of drinking water, right?
Yes, yeah.
One, just all that clay in it, the reason why it's so white would make it a very difficult surface water to drink. But I just wanted to clarify that. But it's all that clay that I find even more surprising, that with such a high suspended sediment load that you could keep arsenic in the dissolved state rather than being stripped out on some iron surface on that clay. Mm-hmm. Any comments about that? I mean, it just blows me away.
So this is also what's shocking to me. I think of systems like in Bangladesh, where the arsenic is extremely high in the groundwater. It discharges to a river. It all precipitates on the riverbank because there's oxidative precipitation onto iron oxides, and the rivers have 2 ppb or 1 ppb, like in Vietnam and Bangladesh. So this was the exact opposite system, and I was very surprised. So I would say Ben would answer this better than me. From talking to Ben and what we've discussed is, and I think Ben's thinking is that it's the high alkalinity of the water, right? That's keeping it in solution, Ben, and desorbing it, carbonates and complexation. That's kind of Ben's hypothesis. It makes sense to me, but Ben would definitely be able to touch on that a bit more clearly, I think.
We certainly have seen that in experimental systems and never been able to describe the chemistry precisely with a real equilibrium constant. I would add, although people aren't drinking this water, Steve, I think the real point is this water is essentially equal to the water that people do drink.
Yes, yeah.
It's exchanging with the water that's in the shallow aquifer extensively. So if you actually look at the chemical composition, it basically matches the water people do drink. So
the groundwater that people do drink. I was just making the clarification because there are public water systems that are taking out from surface water, and this work doesn't say anything about that surface water in those public water, those small community public water supplies.
Yeah. That definitely right. Yeah, this is a nice insight into the source water, which is groundwater for this area. The river acts as a drain and gives us insight into that. Absolutely.
Yeah. No,
it's a good point to highlight.
When the river reaches to the Missouri River, how are the arsenic concentrations at that point? Do they remain high? Like, is all this arsenic reaching the Missouri River?
I think it's low. Just like a physical hydrology, it's a fantastic question. The White River is pretty low flow for so those numbers are I think on the flows I was showing, it's 10 to a few hundred cubic feet per second, which is shockingly low. I think of little creeks around here having that, and this is a river that drains the better part of a state, a huge state. And I think of little creeks in New York that exceed that. So it's a pretty small flow to input into the Missouri. So it probably gets really diluted. But I haven't looked at the concentrations in the Missouri, so I don't actually know. It's a good question.
Yeah, and please, everybody, feel free to ask questions if you have questions.
Hi, Mason. I have a question. Excellent talk. I really enjoyed it.
Oh, thank you.
I have a couple of questions. The first one is, I'm wondering if you can find any direct evidence of the potentiometric surfaces around the losing part of the stream that supports this idea that actually groundwater is the stream water is recharging the groundwater in that segment, because that would be a direct evidence that it's happening.
So, sorry.
The second part. The second part of the question is the correlation between arsenic and sulfate. I'm wondering if you can rule out gypsum dissolution in these waters, because there are layers of gypsum in that area, and also gypsum is quite common in any evaporative regime. You could have quite a large contribution of gypsum dissolution from.
Both are great questions. So I guess I'll take the gypsum one first, and then I'll go to the other one. So I have to look at that. We do have the calcium measurements, and then there are other sources of calcium, but it would still be good to take a look at that and see how that relates, and see if we could subtract out a potential gypsum source based on calcium concentrations. So, Ben's saying it's undersaturated with respect to gypsum in most cases. So maybe we're not in contact with gypsum, but it would be that's a fantastic point and worth taking a look at. And then for the first question, it's a great question. And so actually, I have this information. I didn't put it in the talk. There was a paper that came out about a year ago, and they actually did a really nice job looking at essentially most stream reaches across the United States and trying to find the nearest groundwater well. And so I did grab that. And for these reaches, they were generally, the water level in the groundwater was below the stream, supporting this. The one challenge or thing here is it's going to be dynamic in time in these systems, but it's a great question. There is a paper, it was in Science or Nature, and Giseco, a really cool paper. They got thousands of wells across the US and then compared them to stream bed elevations. And so we did have a lot of losing reaches on the White River where they had data. And then but it would be worth looking at. They just looked at a snapshot, but I could pull the groundwater wells that have continuous measurements if the USGS has. I'll take a look, and that would be good to look at and see seasonally how that could vary to further corroborate this.
I have a question, another question about, with this mobilization of the arsenic and uranium and the distance from when you sample at the beginning and then it goes up, does that help us in any way to know where is it coming from? You mentioned it's the groundwater, the evaporation, all of that, but could there be a mobilization from some of these more contaminated areas, like some of the mining areas? That's something that the communities are very kind of concerned. That's what they want to know. So does your data help us in any way to answer that question?
So, oh yeah, it's a great question. So yes, it could. If I would have to, I haven't looked at that specifically. And so if we were to look at 2 points, like just say there was like an upstream and a downstream point, and then in between them we have a mining area, we could look at like, is there a greater rate of increase in that area as opposed to 2 other locations? So that's I just wrote a note to look at that, but I have not looked at that. But absolutely, and I guess the one of those final slides that I was showing, where we were looking at those like how much could be explained by evaporation, and so I'll just quickly screen share again. So like this kind of slide here, where it was looking at how much could be explained by, can people see my screen? Yeah. How much could be explained by evaporation? So for instance, for arsenic here, there's higher concentration, change in arsenic concentrations than could be explained by evaporation alone. And so I need to plot these on the map now and just to see which ones deviate most from that line, and then maybe they're near a mining area, and it could explain that, or it's an area where the river was gaining a lot, and that would explain high arsenic or uranium groundwater in that area. So there are ways we could tackle that, I think.
Related to that though, Anna, one thing that shocks me about these data is many of these pairs start off of the reservation and go on. So if you actually think about what that really means, it's kind of an amazing Superfund related result in some ways, right? You can have a contaminated site that does not behave like anything else that you normally would think, right? This is the case. Usually the tenet of environmental disasters is you want to be as far away as possible from them, right? Nobody wants to live next to the Superfund site. But in this case, a contamination site gets worse as it goes away. So something that might meet water quality standards at the boundary of where it comes from could fail to do so later on downstream. And so with significant, with some error bars that we're still working on, I would say, by where I mean Mason, it's a compelling idea that actually more of this arsenic comes from quite far afield than I would have ever thought without, as a novel hypothesis. So
and Mike Boland raised his hand, so maybe he has some input also for us or question. Mike?
Yes, good afternoon, Anna. I just wanted to clarify a couple things. The groundwater that is drank down on the Pine Ridge Reservation is limited. There is a pretty large rural water system for drinking water. It's the Mini-Wachoni system that was brought in back in the 1990s and completed in 2014, I believe. And then, precipitation across western South Dakota is pretty arid, at most maybe 15 inches per year. And, in a drought year, it would be very minimal, up maybe 10 inches. So just acknowledge that, the low flow of the river occurs on a regular basis.
Oh, awesome. Yeah, thank you.
Thank you so much. And maybe Mason or Ben or together, can you also provide for the people in the audience here, you know, the series of approvals that you got to do this study and explain a little bit the process, because I think it's very important for people to understand that we are doing all this sampling very carefully.
So I guess I should probably do that since I was the one who did it.
And I think, Ben, it will be good for the future that we always remember to explain this, I think, at the beginning for any study. I know this is not common for you in the hydrogeology world to say these things, but I think it's important.
So these samples were collected throughout the region. So a portion, about half or a little bit more than half were collected on the Pine Ridge Reservation. We obtained permissions to sample through the Research Review Board of the Oglala Sioux tribe for all sampling, regardless of whether it was within the tribal reservation or not, because of it being tribal lands, and have worked with tribal members and our partner, Missouri Breaks, in collecting samples and working with them. And the data ultimately resides with them because of that. And so this is really a project that it has depended strongly on that collaboration between the two groups. And then bringing Mason in as part of our group as well.
Wonderful. Very good. Any other?
And we now have those same permissions for sampling the groundwater on the tribal land.
We did have part of the samples that Mason showed data from include some natural springs and things that we also had permission for as well. But so yeah, we had permission for both.
And the
groundwater wells and others. Go ahead.
The isotopes in groundwater, the water stable isotopes, do you expect to behave in the same way as the surface water isotopes? That this relationship that you showed us will be the same in groundwater, or could there be any difference?
There could be a difference. I guess we'll have to see. I'm going to run all of those this spring and summer with students, and so we'll see. But I would expect some similar behavior here because of the tight interaction between the two. As you go deeper and deeper, it depends on the depth of the well too. If I'm in a 500-foot well, no. But if it's a 50-foot well or a 100-foot well, we might see a very similar relationship. The one big thing that varies a lot more is isotopes in rivers will vary much more seasonally because there's that runoff component and then the base flow or groundwater component. Whereas groundwater isotopes, which is a nice thing, if you sample it once, you usually know pretty well, unless you're right next to a stream, it won't change all that much from year to year.
Mm-hmm. Wonderful. Very good. So I think time is over, but this was a wonderful. Thank you so much, Mason, and thank you everybody for joining.
Thank you so much for having me.
This is our last webinar for the spring and the season, and we'll resume again in September. So thank you so much, everybody.
And I should point out, Mason's wife is due to have a baby tomorrow.
Yeah. So we made it I told her to wait till 4 o'clock today. And she
Very nice baby, very well behaved. We like him or her or already.
Like March